This lecture is going to be about high-dimensional data visualization. Hope you can all hear me. If you can't hear me, let me know and send me a chat. Yes, good news. Perfect. Happy to see that. So let's talk about high-dimensional data. First, I want to tell you a little bit that I redid the last series of lectures because we have fewer lectures, and so I wanted to make sure that we cover the stuff that I wanted to cover. So this time I'll talk about high-dimensional data. Then next time we'll talk about interaction, and at that point you're going to be ready and then today I'm gonna talk about the final project, because some people have asked me that they wanted to know what you have to do. So I'll put a few slides together that tells you what I expect. So this time we will skip the preliminary report. We'll just do the final project proposal, and then it's due in 2 weeks from now. Next time project 2 is due, and the time after that is project 3 is due. And then you work on this, because you need some time to create the final project. So I don't want to drag it on too long, right? So we'll talk about a few other things that you may be able to use in the final project or not. But at this point, you probably know most of it, and then you learn a few more things. So let me see if there's any questions so far. Okay, no questions. So let's talk about high-dimensional data, right? So we learned basically most of our data already were high-dimensional in some sense, or at least multivariate. So now let's talk a little bit more about theoretical aspects and things that are important about it. So basically means feature vectors that have many elements in it, but you have to be aware, and I think I hinted a little bit on the lectures that this can be tricky. And actually most people don't really understand what it means. So if you want to impress people that what you know, then you tell them, I know about high-dimensional data. And lots of people will be impressed by that, because it's hard to understand what it really is. So why is that? Okay, so I thought about this, right? Because when you are a baby, usually what happens, you learn about the three-dimensional world by touching and licking and so on. Then you'll learn about how these objects look, what these objects feel, and then you see them at the same time, and you start building a model of the three-dimensional object as you grow up, right? Eventually, as you get older, you longer have this ability to learn about objects, you learn about objects, but pretty much the dimensionality, 3 dimensions is pretty much understood. And then, but no one's ever showed you high-dimensional objects when you were growing up and you're starting to build these neurons that help you to map things to models in your brain. So nobody showed you high-dimensional objects. That's why you have trouble understanding what it means, right? So don't blame your parents that they didn't show you, because they didn't know either. And besides, you don't want to overwhelm little kids with high-dimensional objects, right? So anyway, that's why it's hard, right? So that's why people generally have trouble understanding what it really means, high-dimensional space really means, right? So we have to build what's called prostheses, right? You have to build methods that can sort of lay it out in a way that you can understand it, right? So the problem with those methods is none of them is perfect. So there's always some things are nicely shown and some other things are not nicely shown. We've seen a few examples of this, like for example, is the linear projections and the nonlinear projections, parallel coordinates. All of these show you certain aspects, but they lack other aspects. And we'll talk more about this today. Okay, so there's also something called object permanence. Basically, this comes from this, that you create a mental picture or remember objects that you have briefly seen. And that sort of helps you with being creative and abstractly thinking. Of course, no one shows you high-dimensional objects, so you don't really remember them easily, right? So that's why we're teaching in this class how to look at them with 2-dimensional primitives and try to understand what they look like in high D. So one very basic thing with high-dimensional space, sharing something. Oh, Oh, I'm so sorry. I don't share my screen. Oh my God. Okay, so let me share my screen. Sorry about this. Thanks for telling me. Now I'm sharing my screen. I'm sorry. I'm sorry. You didn't miss much. You missed this little baby here. Okay, that's all you missed. And then this plan, right? So very much didn't miss. Sorry about this. I have to get better at these online lectures. So, okay, but now it's getting interesting. Okay, before all I was lots of words, but now I'm actually showing you something. So can you see it? Can I see the chat? Chat. Okay, now you see it? Okay. Can anyone say yes? Then you see it. Okay, thank you. Okay, cool. So let's talk about high-dimensional objects and the curse of dimensionality, okay? So, okay. So basically what happens is when you did this, when the number of dimensions goes to infinity, if you have a cube, but now it's a hypercube with n axes, right? If the side length is L, diagonal is D, volume is V. When the side length is greater than 1, then the volume goes to infinity as n goes infinity, the number of dimensions. When the side length is less than 1, actual volume goes to 0. It's also very interesting, right? And when the side length is 1, the volume still remains 1. It's the unit cube, right? And nevertheless, the diagonal goes to infinity. Okay, but the real problem is that it's very sparse, very, very sparse. You just have a hard time to fill it with points because, you know, eventually because it gets so large, right? It's very sparse. And actually that is really some fundamental thing with the curse of dimensionality, right? That it gets very sparse. There's actually an equation that goes with this. So basically what happens is the most points are here in the periphery. Very few points actually in the middle of this hypersphere. That's just what happens. So in a sense, in essence, this sort of this space kind of looks like a hedgehog, right? The points are really in these spikes, as n spikes, and then, you know, and then to the power n spikes. And these are corners of this high dimensional space. And this is the center, this middle area, right? So a point may be here and this spike here and then another spike, and they're all the same distance away, right? So it's really hard to figure out how far points really are from one another because they're all equally far apart or equally close, unless they're in a dense cluster. Of course, then you can easily determine it. So this is formalized by this equation called the Bellman fundamental equation, which is Bellman's equation. Okay, so basically what it tells you, a point, the distance to the maximum number, the maximum distance of a point to another point, and the minimum distance of a point to another point is basically, if you normalize it by the minimum distance, basically goes to 0. Basically what it means is really, as the number of dimensions increases, what happens is that the furthest point is almost the same distance away than the nearest point, which is very puzzling, right? So it's really hard to really figure out the nearest neighbor when you're in high dimensional space. If things are in clusters, of course, you know, sort of know what's in the cluster, but even the description of a cluster can be sometimes very difficult. It's even hard to really describe what is a cluster and what is not a cluster. You know, where is a point inside a cluster, or is it not? Or is it an outlier? Once n goes beyond, like, let's say 8 or 10, it's hard to figure out. So I want to give you like a little bit of an example, okay? Like to give you a little bit, to show you what this means, right? So for example, if you look at this one-dimensional point cloud, right? So it's like, you see, you know, points, you can see clusters, you can see outliers. There's like a cluster here, another cluster here. These guys are a little loosely distributed, but you can sort of see, you know, and you can figure out who is your neighbor and who is not, right? When it gets 2D, let's just say these points are projections of a two-dimensional point cloud. You know, once you have more dimension, you know, you spread out. It's kind of like your apartment, right? When you have a small apartment or it's just a room, everything's sort of tied together. Once you buy an apartment with 2 rooms, you start like, you know, using both rooms, and it's harder to find where things are. Then when you buy a 3rd room or a 4th room or a 5th room, you have to start really searching, right? Because then you don't know anymore, where did I put those car keys? Where do I put these socks, right? It's hard to find, right? So 2D always spreads far apart, and 3D even more, right? Gets even sparser, just by the nature of things, right? Because as you expand out, so just think about like 5D, ND, things get very, very sparse. All of a sudden, it's really hard to figure out, is this point now close? Is it not? Are these points further away? You get the idea, right? So indexing also gets very expensive. So some people may think, okay, we can just, to store it or to index it, I can just take my space and make cells out of it, so then I know all the points in this cell must be neighbors, all the points in this cell must be neighbors. I can just count the number of cells apart, like this cell in here and this cell here, they're 5 cells apart. Sounds simple, right? So all of a sudden I have a way to figure out how far things are, at least on a grid basis. But now count the number of cells, right? So if you have 2-dimensional space, you already have 256 cells. That's no big deal. Okay, I can store 256 cells in 3D. And this is only 16 by 16, right? This is actually not a very good resolution, right? 16 is teeny weeny, right? I mean, into about 256 or 1024 or even more resolution along a grid, right? Like on a grid axis, but even with 16 cube, 4,000 cells. And then when you have 4D, 65K cells, 5D is 1 million cells, 60, 16 million, 7D, 268 million. And 7D is really not much, right? Let's think about 100D or 50D, right? It's impossible to create a subdivision with cells. Anyone who proposes that is out of touch with reality, right? So don't believe anybody who can say you can use a grid to index high-dimensional data. You cannot do that. You actually have to really find the neighbors by computation or by very smart nearest neighbor methods that sort of figure out where things are. Even a KD tree, forget about all of this. This doesn't work, right? Have to really somehow find a way to figure out where your neighbors are. And I give you a few ideas, and there is better ideas. There's a lot of ideas around that can be used, But in the event, you're always going to fall victim to the curse of dimensionality. Every time you add dimensions, it gets really difficult to find. You navigate your way around, okay? So clustering can help. You can sort of start putting things close together, but clustering is also difficult. But anyway, there's always some methods that can help you, but you're never 100% sure, right? So that's why visualization comes in, right? Visualization can help you. The eye can figure it out, what goes close and what not. You can decide on your own what should be close, what should be not, right? Don't let an algorithm decide that. Look at it with your own eyes, and then you can make the decision based on that. So, okay, so turns out it's an exponential growth in number of dimensions, right? Really, as n grows, this goes in exponent, right? So it's basically an exponential growth. And so you know about exponential growth, right? So things just become very, very difficult with just a modest number of dimensions. Okay, so understood, right? So now let's talk about parallel coordinates. Okay, we've talked about parallel coordinates, and then we understand, you can take like say 7-dimensional point and like a car, for example, you can mark the value it has on one dimension, which goes with a mile per gallon. Then you mark the car's value for cylinders on this axis, horsepower on this axis, weight, acceleration, year, and origin. So you mark them and you connect them with this polyline, and you basically have a parallel coordinate representation of a car. And then you can have more cars, and then you got this sort of crazy mess, and then you can do some clustering and then group them into cars with high horsepower, powerful cars with medium horsepower, medium powerful, and these ones that are not so powerful, but the ones that are economic, right? And then so you can sort of get a little bit of sense out of it. We talked about this before, right? I just want to bring back the memory of it, okay? And should be interactive. So want to tell you a little bit more about how to read these parallel coordinates. Okay, we did talk a little bit more about basically, a correlation, negative correlation in a scatter plot looks like a bow tie in a parallel coordinate plot. Okay, this is basically when a point has a high value in one dimension, has a low value in the other, right? And when a point has a low value in one dimension, has a high value in the other. So they basically cross here somewhere. And this like this very characteristic bow tie pattern. High correlation, positive correlation, looks like this, right? So basically when one has high value here, has a high value here as well. Okay, so this is by perfect correlation. Perfect negative correlation, perfect positive correlation gives perfect pictures in parallel coordinates. And when it's not correlated at all, you get this sort of, you know, random overlapping lines, right? So if you know a little bit about parallel, if you know this, you can actually diagnose parallel coordinates this way. Whenever you see a bow tie, you know, aha, you know, must be negative correlation. When you see this kind of parallel arrangement, you know it's positive correlation. And when you see this kind of thing, you know there's no correlation. So this basically helps you read a parallel coordinate plot. Then you also, basically here is a little more, right, on this. Very negative, very positive, right? There's also intermediate, you know, this official score, you know. So, and, you know, this goes with the different correlations. Okay, this is the official score. This is the highly negative and highly positive correlation. Not quite perfectly correlated, but you know, here's zero. You can sort of see these bow ties start to like get a little wider, and then they're completely gone, right? And so on, right? So you sort of see this is not quite a perfect bow tie, and it sort of dissolves until you go here. You know, here's messy, and then it starts to organize, right? It's a really nice story you can see, right? That the bow tie starts to evolve into this perfectly parallel patterns. And if you have fewer points, you don't see it as well, right? If you have only 10 points, you don't see this as well if you have like 160 points. So you want to have a few points to really see the pattern evolve, right? If you don't have a lot of lines, you don't really see it well. These are the scatter plots. Again, if you don't have a lot of points, hard to really figure out how the correlation really is. It's always good to have more points, right? Because, and that's a standard rule, right? Correlation is the confidence you can have in a correlation pattern, the p-value that you can measure, you know, that you can measure is actually a function of the number of points. As you add more points to the point cloud, the p-value gets better that you can compute on a correlation that you compute, right? So the more points you have, the more confident you can get on the correlation, that the correlation is really what you computed, okay? So it's a matter of points, right? So as you add more points. What turns out, people have done user studies, you know, that turns out that actually when people were shown plots that showed that the scatter plots and parallel coordinate plots, and they were asked to estimate what the correlation might be. Turns out twice as many people, so the correlations actually levels that could be detected were twice as, the separation between different correlation levels was twice as good with the scatter plots than with the parallel coordinate plots. So if you want someone to estimate correlation, it's still better to use scatter plots over parallel coordinate plots. But parallel coordinate plots have other advantages because it allows you to really join many variables in a single sort of line, right? Like here, right? You can tell, you can have many variables aligned like this, and you can sort of follow them. You don't have to look across different scatter plots to see what's going on, right? So everything has a pro and con, right? And I wanted to show this with high-dimensional data visualization, because everything has a pro and con, right? Parallel coordinates don't show you correlations as well, but they do, they can, but not as well. Scatter plots, on the other hand, show you correlations better, but they don't allow you to really see n dimensions at the same time, right? You know, you have to build a matrix of scatter plots, and we're gonna talk about that too in a second in another slide. So another problem with parallel coordinate is really when you look at these parallel coordinates, right? So there's many ways you can order those axes. You know, why do you want to show mile per gallon next to cylinders, next to horsepower, next to weight, next to acceleration, next to yield, next to origin? Why not show the weight next to mile per gallon? Might be that's interesting, you know. So you have to reorder it. It's really hard to figure out the correlation of mile per gallon with weight, because there is cylinders and horsepower in between, right? If you really want to see the correlation of mile per gallon with weight, you have to bring the weight axis towards the mile per gallon axis, right? They have to actually put them next together. Then you can really see that, right? Then you can really see this pattern as I show it here, right? If this is weight, if this is horsepower, this is weight, you can see easily the correlation of horsepower and weight. But if the weight is somewhere else, hard to see. So this is basically a very conceptual problem with parallel coordinates, right? The need for axis reordering. Okay, there's n factorial ways to actually order those n dimensions. Okay, because n factorial ways. So think about it. How many orderings for 7 dimensions? There actually turns out to be 5,040 orderings. Okay, 5,040. That's a lot of orderings. If you want to explore all of them, good luck, right? Have fun, right? It's a lot of orderings to explore, right? So, but since you can see relationships across 3 axes, because these 3 are next to one another, right? It's actually n choose 3, okay? n factorial over n minus 3 factorial over 3 factorial. It actually turns out to be only 35. So it's a little better. Still, 35 is a lot, but it's a little better, but still, I don't think anybody wants to try out 35 different orderings to figure out what's going on, right? So, still a lot, right? So we need help, okay? So I show you like something that can help you, okay? And I think I talked a little bit about in the lecture, but I'll now bring it a little bit closer. You can actually use correlation, okay? We talked about correlations, right? This equation here, that this is a typical correlation plot. We've seen it before. Very highly positive correlation of horsepower and weight. And we know that, right? The more horsepower your car has, usually the weight is more too, because you need to keep it on the road, right? Actually, 0.87, okay? So, and then there's the parallel coordinate display for it. Well, it's pretty good, and it's informative when you see this. Oh, that's interesting, good correlation. So I learned something by looking at that, right? So building the correlation matrix. So here's this correlation matrix, right? So now this is the correlation matrix. And this is just some random parallel coordinate display, right? Just a data set with, I don't know how many dimensions, lots of them, that is here. So, don't see much, right? There's some correlations here, but not much. I can see some clusters of points, but it's disturbed by other things that are not really clear. But this is a real world case. It's not hard to see anything. So now you start to like move these axes around until you find something, right? Good luck, right? No one will do this. So what you can do instead, you can take this correlation ordering, right? You take each data point and create, like, encode the distance of these data points with a correlation value. Then you do a mass spring system like this, okay? Mass spring system like this. And what it basically does, you try to minimize, basically you force it to have points that are closely related. So each point is a dimension, right? Each point is basically one pairing, right? Like basically you try to take these pairings, and each pairing is a connection from before, right? Each pairing is a connection. Okay, so if a value is big, if a correlation is high, then I want to make that distance, that spring very small. And if the value is very big, the correlation is small, the correlation is low. I want to make a spring very large, right? And I'm starting to optimize this until the mass spring system has a low energy, right? Has low energy. Okay, so basically those distances are perfectly preserved. So now, points that are close together have a high correlation, or a low, or 1 over correlation, and points that are further apart have a low correlation. Okay, so I got these clusters, so I can see, okay, there's a lot of variables highly correlated. Here's another set of variables highly correlated, and some more, right? So, and some more that are not, right? So now what can I do? Okay, what can I do is I can run the traveling salesman program on this, but I can now connect them, right? I can say, okay, these guys are like small, they're like low connected, so I can basically run this traveling salesman algorithm that finds the shortest path among all these points. So first the traveling salesman will visit all of these. Then it moves to the next cluster, visit all of these, move these points here. So now basically, okay. Then I can use this. I can just basically order the axes based on the distances. I just go here, start here, and start taking the axes and order them. Then I order this one, take the axes, order them, and so on, and create this kind of ordering, right? So this here are the first cluster of variables. This is the second cluster of variables, and these are the ones that are not correlated at all, right? So really see this, right? Just by taking the correlation matrix, organizing the points in terms of the correlations that they have, right? Run this mass spring model on it, or this force-directed diagram, right? And it's basically nothing but an MDS display, right? An MDS display on the variables, right? And then just take these dimensions and order them, and then all of a sudden get a really nicely organized way to look at these points, look at these variables, right? So now I clearly see, okay, these variables here, you know, there seems to be two clusters of points, right? There's clearly points that have high values everywhere and points that have low values everywhere. And then here, the next set of variables seems to be three clusters of points, right? There's points that have high values here, points of medium values here, and points that have low values here. And then here, and the other ones, right, there's not much to see because the variables are not correlated. So really, I don't really expect any clusters, right, because there is no correlation among them to begin in the first place, right? So this basically simple technique helps you to overcome this problem with the factorial search, right? That this n factorial search to figure out an optimal parallel coordinate display, right? So this is really a nice way to do this, okay? Then you can say, like, this is number one, number two, number three, right? So this is cluster one, that's number two, cluster number three, right? So you can segment it actually, right? So now that we have this correlation network, okay, or this network of vertices where the vertices are the attributes and the edges are the correlations, okay, now I have this, right? And I make the positive correlations, I color them in green, negative correlations, I color them in red. I can learn something about this car data set. For example, I learn that the width and the height, the weight, are positive correlated. Makes sense, right? When a heavy car is probably, you know, wider, you know, a white car is probably heavier. The price turns to be negative positive correlated with weight. Seems to have to pay more money for a heavier car. Like a Mercedes costs more money and is heavy than a Kia, small Kia, right? And then, which is a lightweight car, and or a smart car. Then price and Marber-Gellner is inversely. So price and weight is okay. No, sorry. Price and cylinder is positive correlated. Okay, I have to pay more money for a car with more cylinders. Makes also more sense. Horsepower is positive correlated with price, right? So more horsepower, more price. And turns out horsepower is negative correlated with Marber-Gellner. Makes sense too, because we learned that, right? Because you have a car with more horsepower tend to have less Marber-Gellner, right? Because they eat a lot. But also, interesting enough, the price is negative correlated with Marber-Gellner. Turns out when people buy more expensive cars, they don't care about the gas consumption as much, right? Because they have enough money to buy gas, right? You can get this from there. You know, the Marber-Gellner is also related this way. We already talked about this. So, okay, so basically just by looking at this overview, you can learn a lot about the data. Just look at this map, right? Basically, this map tells a lot of story, right? Tells a lot of story. Then you can take this map and say, okay, I'm only filter them by strength. You know, you can just say, have a little slider and roll it down a little bit and only look at the very strong correlations. So you can clean it up a little bit. So that's interaction, right? And then I can do attribute. I can click on an attribute only and only look at all the variables that are related to this attribute, right? So these are all interesting interactions you can do on this kind of plot, right? So you know, there's other ones, right? You can, you know, there's this one here where you look at the subset attributes, how they're intercolated, right? You can basically say, okay, I'm only looking at these attributes and really look at the network that exists among these attributes. So, you know, so there's basically various ways in which you can interact with this kind of network of variables, okay? Then you can also You can also now, you may say, what about what happens if you have like 100 or 500 dimensions, right? What are you gonna do, right? When you have five, so there's gonna be very complex kind of look of, you may want to only focus in on this particular one or this particular one, maybe, what you can do. So what you can do is something called multi-scale zooming, okay? So multi-scale just means you're gonna zoom in at a particular subset of variables, okay? And only look at them in the parallel coordinate interface. So I'll run this little video, so now you just go here and then basically have a screen. On the screen, basically, just all you do is really you take the mouse and roll the wheel and then sort of zoom into a particular cluster, and then only those dimensions are shown, right? So this is basically a typical brushing and linked operation, right? Where you brush on a certain part of the visualization here with the mouse or zoom in, and then it's linked to the parallel coordinate display that reacts to it, right? And this is actually something I want you to do for the final project, right? I want you to implement, you don't have to do it with this kind of primitives, but I want you to implement brushed and linking, right? Where you manipulate one display and other displays react to that, right? And we'll talk about that in the final project, but in the sheet that I'll talk about later on. And you can go out and see everything again, right? And you can also zoom out more. And what happens now is basically, what happens here is that basically now all these points that used to be like this get now reduced to a single point, right? Basically like this, right? So it's now just a single point. So basically all the attributes are basically abstracted into a single attribute. And then only this one attribute is shown, okay? So this is like very truly multi-scale, right? You really reduce all this detail and just have only one point that represents it, right? So this is another, example. So all of this is multi-scale. So we published all this in a paper with my PhD student, former PhD student, Shivan Zhang, who is now at Facebook. So you can read this paper. I don't have the reference here, but if you want to know, I can give you the link. So now let's talk more about parallel coordinates and talk more about correlation and talk more about that correlations usually don't just, that they're usually very confined to certain areas, okay? So correlation strengths can be improved by constraining an amplitude's value range. So let's talk about that. Look at this one, right? For example, here, this these two attributes, price and sales. Okay, let's assume we have a store that has or a manufacturer that has products at different price, and they observe different kind of sales. Okay, the product, it has different price because it has more or less features. Okay, of course, it's not just a single product that you upsell, right? It's basically a price that you price higher or lower. Each of these basically is really a slightly different product because it has more features. So when you look at this overall display, right, what you're going to basically learn, and I represent these remember, I represent each attribute by a vertex, just like, remember I talked about here, right, where each attribute is a vertex or a node, right? So I replace each attribute by a node and put them like this. Okay, so price has a high variance, that's why I make it a little wider, and for the diameter a little wider, and sales has a low variance, okay? But don't worry about that too much, okay? So now there's no correlation, right? I don't have any link, right? They're not correlated at all. But if you take the price down, like if you just bracket it to this particular subrange and only observe the sales for this particular subrange, you find out, wow, there really is a positive correlation here. Like lower price, less sales, higher price, more sales, right? And positive correlation. And this is interesting. So it turns out when I do marketing or product development, right, or want to plan my product development, I know, okay, these products that are higher priced, they sell better, then apparently people really like what I'm adding, right? They really like what I'm adding, okay, to my product. They don't like the bare bones product. They have a little more extras. They buy more. But then if I look at the high-priced products, I find out actually there's a negative correlation, right? It's like this bow tie. Remember this bow tie, right? Negative correlation. So turns out lower priced items sell better. The really super high priced items, they don't sell at all, right? So from this I learned, okay, well, there's a limit to things, right? So, if I go in the higher end products, those really super products there, when they're really high priced, golden knobs and things like this, the people don't really care about this, right? They don't like the bells and whistles here, right? So basically, maybe I don't even want to continue that line because no one buys it, or maybe I don't really pitch it that much because people don't buy it, or reserve less catalog space there because people don't buy it, right? Whatever, right? Or maybe I have to pitch it more, I don't know, but that's anyway, you get a little bit insight from this. So what I want you to learn from this is it's really important to look at correlation within certain brackets, right? Don't just look at the overall. That's what most people do. They take like two variables, look at overall correlation, say nothing going on. But you really you can use visualization of parallel coordinates, right? You can take the parallel coordinate slider, go down and see what happens, or go up and see what happens, right? Just take that variable, move up the range and see what happens. And or take this variable, move down the range and see what happens and get some insight, right? So this is interactive visual analytics, right? You learn something about the data by playing with it, right? Using parallel coordinate to look at some pairs. So, you can go to another pair and then just see what happens. Just see what happens, right? And then you can really learn something about your data, right? And this, you can even see this, you can even go to another axis then and see something to happen, right? Because these lines will be across the entire display, right? So, but anyway, so hopefully, shows the power of parallel coordinates and show the power of interaction that you can learn something about your data. So the next thing is these correlation plots, what you can learn from the correlation plots themselves, right? So you have this data set here of 50 US colleges, okay? This is basically a fusion of two data sets, the US News academic rankings and a data set from the college prowler that it's called now Niche, which is essentially a survey on campus life attributes, okay? So there's like two, remember what I told you about, like you should take multiple data sets and fuse them together because they give you complementary information about the data, about the whole subject of college, right? Here you get academic aspects and here you get the life quality aspects, put them together, learn more about the colleges. So let's put this together in this correlation plot, right? In this force directed layout or mass spring layout, where closer mapped nodes are highly correlated and further apart nodes are not so much correlated. And here I basically used the absolute value of correlation, right? Not, basically didn't matter negative or positive correlated. They were just closer when they were correlated or not, and not so close when they're not correlated. And I just indicated positive correlation by a green line and negative correlation by a red line. So I learned like PhD per faculty, the colleges that have a high PhD per faculty, they tend to have high academic value, right? They usually, but they also charge more tuition, have a higher score in US News, okay? So when faculty members have lots of PhDs, that turns out to be a better school, right? Because in Harvard, those faculties usually have a lot of PhD students. I also have 8 to 10 PhD students. Apparently Stony Brook is a pretty good school, according to this. Academic value is related. So, because, there is a lot of science going on and then you get a good education, right? For graduate, at least definitely for graduate education, right? So then the tuition has something to do with this, right? And then here, there's also another cluster here, location and nightlife and population nightlife. So higher college towns with more population tend to have a better nightlife. You know, so Stony Brook doesn't have that good of a nightlife because no one lives there, right? So maybe that's the reason. Turns out, so income is higher when the population is higher. Turns out, so athletic, when the income is high in this particular area, athletic turns out to be not so good. Athletic meaning the college athletics, right? The college athletics. But when the income is low, then turns out the athletics program is pretty good, right? That's very interesting, right? And it also turns out athletics is really one of those attributes that really links the academic cluster to the overall to the town where the college is, right? Because you know athletics is high, academics turns out to be lower, you know. So basically, Harvard doesn't have a really good football team, right? But you know other universities are not so good academically, but have a really good football team, you know. So it turns out to be that way. Not all of it. There's of course outliers, just overall, generally speaking, right? Not like perfectly speaking, but generally speaking, right? So you can see a lot here, right? You can see this cluster here. This is the academic cluster. You see the more the you know, safety, some good with location, nightlife. When the nightlife is good, safety is not so good, right? You know, well, you know that happens. Safety is not so good. Transportation is better, right? I don't know why that is. So anyway, and then there's this PhD by faculty and academia is interesting here. I just highlight a few things. Income and athletic is interesting, and that this athletic links together the academics. Okay, so just try to sort of highlight certain things here. So I already talked about this. So now let's talk about scatter plots. You know, so we've talked about these correlation plots here that try to give some insight into how the variables all go together. So when you do a visualization, if someone gives you a data set, you know, I really recommend to create such a plot, right? Because it gives you really a quick way to figure out what is really going on, right? Which factor is correlated with what other factor. Sometimes you see redundancies, you know, then you may be able to just choose only one variable over another. You can sort of get a little bit of an idea how to arrange a parallel coordinate display, because parallel coordinate display is a really nice display because it really shows you everything at the same time, right? So oftentimes parallel coordinate displays oftentimes parallel coordinate displays and these attribute layouts really go well together, right? They show you the way the attributes are arranged, and here related. And here you see how the data are related, right? So you get basically get both at the same time. So I really recommend, if you do like a visualization, this plot is really good to have, right? Just compute a correlation matrix, use a mass spring layout, plot them, right? And easy, right? Very, very easily done. So now let's look at scatter plots, okay? So here. So scatter plots, basically, we learned about this, right? It's projection of data items in a bivariate basis of axis. You know, here it shows weight and mile per gallon. Clearly negative correlation going on, right? Clearly seen. A little bit of a polynomial, not perfectly linear, right? A little bit curved, okay? But only visualization can show you this, right? And so, but now, how does 2D projections work in practice, right? Like, let's say you don't usually have only, you know, 2 dimensions, but you have like n dimensions. Let's say, you know, for the car you had 7, right? So, like when you look at it, an n-dimensional point is really described as this n-dimensional vector, and then this 2 orthogonal axis vectors are like this, right? These are these 2, you know, vectors. If it's simple, right? It's just one of them is 1. A1 is 1, like, you know, if it's a simple axis vector, right, only one of these values be 1 because it's the one that is the vector, the axis, the dimension itself, right? A1 could be weight, B2 could be horsepower, right? Then this will be 1 and this will be 1 and everything else will be 0, right? And then basically you project, the projection is essentially just, you know, this dot product of this of a point vector with the axis vector, and you do basically usually use 2 to get a 2-dimensional point plot, right? Then this is what happens, right? The T is the transpose. Okay, so basically you have this 3-dimensional space, you project it in this space A and B, and you get this scatter plot. Okay, So now, you know, this projection causes inaccuracies, and I want to like build up this notion of projection ambiguity, right? To give you a little bit of a sense to appreciate, you know, this linear projections versus nonlinear projections. Okay, so you know, so here you have this projection, which is a linear projection, right? It's just linear, right? A dotted with xt, B dotted with xt, right? You know, that's basically just it, right? It's a linear weighting, right? Just the dot product is a linear weighting. Okay, then you project this here, right? So, but now when you look at it a little bit more closely, you'll see that this point here and this point here mapped really close together, although they were really far apart, right? This like they were really far apart. Now they appear close together because this other dimension C didn't really matter anymore, right? So you know, this could be weight and horsepower. This could be price, right? So these points here are very close together in weight and horsepower, but they're very different prices. But you don't see that, right? They seem to be the same, very similar cars, but one is a Mercedes and one is a Volkswagen, right? They really are not really, you know, but you don't see that from just plotting A and B, right? So this is what's called projection ambiguity, right? Whenever you project something linearly, you're gonna get these ambiguities, right? Because you basically you're occluding something, right? So we learned about PCA that tries to reduce this or minimize this by figuring out projections that maximize the variance, right? Like here, right? Then you create these biplots, right? Try to find projection axes that are basically, this is the first PCA vector and this is the second PCA vector, projector points into these spaces. Then you sort of optimized the spread of the points, right? Because you try to optimize the variance that this set of points exhibits, right? But there's still, when you looked at your scree plots, right, there was always maybe a third or fourth or fifth PCA component that still had significant eigenvalue, right? And then you basically didn't consider that, right? So, you know, you basically didn't consider this part, right? Because, you know, so there could still be a case where this purple point and this blue point here, they seem to be close together, but they're really not, right? Because there's like this other third PCA dimensions that you know, didn't consider, right? And this is really the problem, right? Because PCA, just like they're bilinear projections, right? Projecting ND into 2D by linear transformation. And when there's more than two significant PCA vectors, that's where the scree plot comes in handy, right? When you look at the scree plot and you can see, wow, there's only two significant PCA vectors, then this biplot is not bad. But once you have like 3 or 4, then can't trust it perfectly, right? Then these remote data points might project into nearby plot locations, but you know, they may not be really truly nearby, right? And then you have this ambiguous plot. And if you start to like bet money on this neighborhood, right? You say, oh, well, they're similar, so I'm gonna buy both of these stocks. They're actually not the same, right? Because you forgot about another aspect of this. This could be very, very dangerous, right? So you gotta really be careful with this. Always look at this PCA scree plot to gauge accuracy. But even then, if you know there's a third one, what are you going to do, right? What are you going to do? Because the PCA may not be a best display for that, right? So maybe you want to look at, the, a parallel coordinate display next to it, right? To see, like, really appreciate those things. Or you can make these biplots interactive. So here's like something we developed a while ago. It's called the, this interactive biplot. So what we did was basically in this research that I did with a student named Bing Wang, who is now working at Google. This was like maybe 4 years ago. We call it the Subspace Explorer. So what happens, what we did here is this is essentially a biplot. Okay, this is essentially a biplot. But it doesn't quite look like a biplot, but it is. Because all we did basically, we didn't plot those axes. We didn't project the axes into this biplot space. We basically, instead of showing the axis, we showed the axis label on the periphery. So when the axis label is more visible, then the axis vector was longer, right? So this is like, it's visible, long, has a very, this basically, this cost, this is a sales data set, this variable cost has a very high, is a very well exposed in this scatter plot, okay? Leads one, also number of leads, also well exposed. These other ones are not so exposed. Expected RI is exposed. Then the other ones are not so exposed, okay? But then you sort of see whatever I see on the screen here, this green cluster and this purple and this blue cluster. This blue cluster here has more leads one. These blue salespeople had the lead loss, and these ones did it at a lower cost, right? And so on. And these are very similar. These purple and these red, blue salespeople were very similar. These won a little fewer leads than these, so on, right? So, but there's, it's a glass cluttered view by putting it around, right? It's like a design kind of thing. But there's more to this, right? So okay, why is not? So what we did basically, we did the Subspace Voyager, which takes these high dimensional spaces and puts them in low dimensional subspaces. Okay. So now I want to introduce to you this concept of subspace. And what you have here is essentially a three-dimensional subspace. Okay. Three-dimensional subspace, basically a subspace that's formed by three PCA vectors, three local PCA vectors. Okay. Initially, So why is it a 3D subspace? Because this ball here is not just a two-dimensional projection. You actually can rotate it. So you can rotate it, right? Because you can rotate it, you can get a little bit of an idea how these clusters work together, how they go together. You can sort of see how much this purple and this blue cluster really overlap, how sparse is it, and how does the green cluster really interact with it, right? You can also see these dimensions as they rotate around, right? You can sort of, that goes along with it. So this is basically a way to now explore not only two PCA vectors, now you can see three PCA vectors. So if you have a scree plot that has three PCA vectors that are significant, you can see it, right? You can now see it. You can sort of see this three-dimensional space spanned by these PCA vectors, which express these variables, right? So they go a little bit in and out of focus because some variables are more expressed in one PCA vector or not in the other, right? So basically what this does. So, but now I want to introduce to you another important aspect is called view optimization, right? So, you can take this basically and rotate around, try to find the view in which the three clusters are perfectly separable, right? Or optimally separable. Yeah, you can go around and look at that, right? Because you really want to separate it, because when you separate them, then you can sort of figure out what really matters to each of them, right? How they're related. So you can do this, okay, by hand, or you can use optimization or view optimization. So when you do optimization, then you can get something like this, right? This is initial view and this is the optimized one, right? So this is the best view you can get for this particular three-dimensional subspace. Okay, the screen. Oh, it's pretty nicely separated. Okay, these are really nicely isolated. You can optimize that. So how you do this? Okay, so the way you do this essentially is there's many ways to optimize it, but I'll show you like one that is really, really nicely, easily programmable and doesn't really require you to do any numerical, optimization. You don't have to compute any gradient search or things like this. It's basically a genetic algorithm, an evolutionary algorithm, okay, called ant colony optimization. Okay, so how does this work? Okay, ant colony optimization is a very attractive algorithm, and I wanted to introduce you to it because it actually comes in very handy because it's pretty general. Okay, so basically what you have in this problem here, right, as you rotate around, right, there's basically a rotation at work, one around the x-axis, one around the y-axis, and one around the z-axis, right? And depending how much you rotate, the x-axis is the first PCA vector, the y-axis the second one, and the z-axis the third PCA vector, right? And you rotate around them and create a view that projects it into the two-dimensional space, right? Also projects the PCA vectors into two-dimensional space, and of course all the other variable axes too, right? So basically you have three interactions, like rotate around x, y, and z, and then basically these choices you have to make. So what you can do is basically you can create this. You can do this ant colony algorithm. Basically, you generate, let's say, 5,000 ants. Okay, and basically this mimics what ants do in real life. So in reality, when ants go to a food source and come back to the nest, they start building these paths, right? Whenever you go in a forest, you never see ants walking around like this, right? They always walk around in a path, right? For some reason, there's always this trail of ants. So, but how does this path develop, right? Sometimes the path is not straight. Sometimes the path goes around and you don't know how it happens, right? Well, actually, you can sort of look at it and you can see the path goes around a rock, or it goes around like a narrow, like some sort of trough. It's optimized for distance, right? So the way this works is basically as ants go to the food and come back, they make choices at different junctions, right? So basically one end goes this way, one end goes this way. And every time it does makes this choice, it leaves a little bit of something called pheromone in it, right? That starts to evaporate over time, right? When an ant smells the pheromone, then it says, oh, this is a really good term to make, right? And then it makes that too. But the pheromone expires over time. So when ants take a long time, the pheromone expires, and then it doesn't last very long. So the ant doesn't to take it, right? So basically, what happens is the way I do it in this particular algorithm, I'll take the ants and let them go loose, and then let them decide how much they should rotate around x. So each ant can make a certain choice, right? It can rotate more about x or less, and then it goes to the y direction. It can rotate a little more or less about y, and then it can rotate a little more or less about z, and it's randomly determined. And then they're going to generate a particular view, right? Each ant basically creates one of those views, okay? And then I can have an algorithm that decides how good a view really is. And I'm going to show you one of these algorithms later on, right? Basically, I can determine how good a clustering really is, okay? Is this a good clustering or not? This is not a good clustering because there's a lot of points that are sort of intermixed. This is a better clustering because not a lot of intermixing happening. So I can come up with a metric that tells me how good a clustering is and how good not. So each ant creates such a view by rotating, around certain ways, right? Each ant rotates, and arrives at a certain point, creates a view, and then at the end, I can measure the quality of this view. Okay, I can measure the quality of this view. I can say this ant here created a particular view like this, and I say, well, this is a terrible view, and then the other ant created this view, and I say, well, this is a great view. And what I'm going to do is I'm going to punish all those directions the ant took. This ant here, the bad view ant took. I'm going to punish those views. I'm going to say x rotations that go a certain degree. I'm going to lower the attractivity for that degree. And the y direction this ant took, I'm going to lower it. And the z direction this ant took, I'm going to lower the attractiveness. For this ant, I'm going to raise it. I'm going to raise the x choice it made. I'm going to raise the attractivity of the y choice it made, and the attractivity the z choice it made. And I'm going to do this for all the ants. And the end, some x rotations are more attractive than others, and some y activities are more y rotations are more attractive than others, and z orientations are more attractive than others. And then I'm going to take another set of ants and let them go through. And then when they encounter such a junction, they already know some some X directions are better than others, and you take this into account when they randomize a direction, right? So eventually, the directions one single directions get more attractive than others, and so on, right? And then all the ants will take that path, right? So basically, eventually, over time, as I have more and more of these generations going through, I'll find out what is the most attractive X orientation, what is the most attractive Y rotation, what is the most attractive Z rotation, and then this is going to be the view that I'm going to generate, this one, right? So by optimization, right? So all I really need is an algorithm, which is the ant colony algorithm. All I really need is a metric that figures out which is a good view and which is not. And then the rest is automatic, right? So in this case, user can just see this view here, say optimize, and then this view will be generated automatically. Okay, so this is basically, a way to help visual analytics, help the user, optimize what he's gonna see, right? So it's still visual, user still in charge, but can optimize the view. And this also works for other things. For example, if you have such a view here, sometimes, because this is only a three-dimensional space spanned by those three PCA vectors, if you have a fourth PCA vector that was also good, right, then you want to reach that subspace, right? You want to go to that subspace. Right now, you're only in those three. So you want to be able to give the user a way to go from this one 3D subspace to another one that's next to it, that has a little more of the fourth PCA vector in it, right? That basically a little more, but really the user doesn't really care about PCA vectors. The user cares about actual dimensions, right? So what you basically do is you let the user, let's say the user sees, this particular variable pipeline revenue, right? But it's not very well expressed in this particular view. The user says, well, I don't really want a view that is more expressed, that has more parallel pipeline revenue in it, right? So basically I have to go to an adjacent subspace that has that pipeline revenue more expressed, right? But where the projection of pipeline revenue is bigger, okay? Oh, sorry. So basically here I show you this, how this program does this, right? So basically all you need to do is take the mouse and point it to this attribute that you like, it moves a little bit, just keep doing that. Okay, and then you should see, right, all of a sudden, before was not expressed, but all of a sudden clusters have emerged, right? A single cluster has emerged. There's a single set of salespeople that have a low pipeline revenue and the other ones have a high pipeline revenue. Just by interaction, basically just by going in another adjacent 3D subspace, then you can rotate if you like, and you have now basically expressed more of the pipeline revenue. So you have, again, interaction that helps you, and an algorithm that emphasizes the pipeline revenue, basically emphasizes certain contribution of a variable, and then that's basically what you get, right? And the projection mechanism that takes the points and projects it into the three-dimensional subspace that is now a little more expressed by pipeline revenue. Still a three-dimensional subspace. You can still rotate it if you like. I don't show that here. But it's a nice way for users to explore n-dimensional space without ever knowing anything about high-dimensional space, right? All you really do is go to the variables that you like to see, and then follow your hunches, right? Follow that you may have noticed that there might be a separation, but you quite can't reach it. So now you can see, like, explore certain variables that may reach it. Okay, so that's like a nice way to act with high-dimensional space. Then you can also save them. You can paint them, and you can save them. Stuff like this. And so there's basically a map of the different subspaces and the way they're similar. Okay, so next, the last thing I want to talk about is about like clarify spatial relationships. With like something that from the volume rendering lecture. And I'm gonna show you how this works. Okay. Sometimes you have this sort of thing here, right? And you really don't know how does it really look, in more in depth, right? Because you have this depth, but you don't really see the depth dimensions also. What you can do is you can use something called depth queuing, where you basically make points. This is a three-dimensional subspace, okay? Where points that are further away from you are more faint than points that are closer to you. Okay, so it's like a little bit of fog in the scene. You can see these pink points are close, and these blue points are far. You know, you can see, okay, well, there's a little bit of structure that I can see. You know, there's a little bit of something I can see in 3D. It's only a depth queue, right? But it's not really truly 3D, right? But 3D we know very well. Remember, we see surfaces all the time. So how about making a surface, right? And make it here, right? So you can just take this point cloud here, which is really unnatural to the user, right? It's really hard. You know, users don't look at point clouds like this. Users can look at shop objects like this, right? So basically now I make a surface out of these points, okay? So, you know, so basically all it does really, how did I do this? And this can be explored, of course, but you can move it around in a trackball again. So how did I make the surface? That's where your lecture in marching cubes, you know, comes in handy, right? So basically what I did here, I took this point cloud in the three-dimensional subspace, make it a grid, and then blur it together. You know, so now it's a little bit of a blurry kind of cloud, right? And then each point now in this grid, in the three-dimensional grid, has a value. And where it's more dense, it has a higher value than when it's not so dense. And then I run marching cubes on it, the one you learned in the volume rendering lecture, and then create an isosurface. Okay, just an isosurface. And this is now the isosurface of this point cloud, right? The purple looks like this, the green looks like this, and the blue looks like this. So I can see how they intersect a little bit, right? I can also see what's like how they look, you know, in 3 dimensions, what shape they have. Of course, I can change the isosurface. I can make them small. I can make them more. I can, you know, I can show more dense areas by increasing the isosurface value. I can show less dense area by decreasing it, right? I don't show that here, but I can. Right? And I can also rotate. So what I want to show with this is, it's always good to know a little bit about volume rendering, because really what it is now, it is volume rendering, right? You have volume rendered, isosurface rendered, this, what used to be just a regular point cloud, right? From information visualization, I now successfully connected information visualization with volume rendering, you know, and here's a real volume rendering display, right? And this is what is called, you know, ambient shading. You know, ambient shading means there's no ambient occlusion, you know, there's no real light source here. What really happened here, basically, I made things darker when they were included areas, and made things brighter when they were in very highly visible areas, right? So you can sort of see really nicely, you can see these occlusions, okay? So it's a nice piece of work. Also Bing Wang did this one, so, okay. So we have 10 more minutes. So I'm gonna go and explain the final projects now for the remaining time. So, you know, we'll continue with this lecture. Okay, next time, it's actually a nice break. You know, this goes in a different direction now. So, you know, so we'll talk about this next time. Maybe if we, you know, but I think we probably, yeah, we'll do the final project now. So let's talk about the final project. Okay, so I made this slide here, the slide set here, to tell you about this. So what the final project really will do, right? So final project basically wants to measure where you can basically now let all the stops out and show what you've learned in this class, okay? So we learn next time, we'll learn about interaction, and we'll learn about dashboards, and then you really know everything you need to know, right? That basic things that you need to know. And you really, what I really want you to do is you want to have a real world problem, and you want to use an interactive plus visual plus analytics approach, right? Which is actually visual analytics, right? It has to be interactive, it has to be visual, it has to be, and there has to be some analysis underneath, right? Python based, okay? So this is the interactive part, this is the D3 part, this is the Python part, right? Well, some things you can compute in JavaScript too, right? So basically, it really has to connect together, okay? So the first task is find a real data set. and the challenge that interests you, right? So you can maybe already found the real data sets that you like. Maybe you don't like the data set that you found for the first labs. Find another one. I'll give you some idea on good topics in the next slide. Okay, and then determine what aspects you would like to analyze and how. Okay, this is what you're going to write in your report, in your proposal. Okay, that you're going to deliver in 2 weeks from now. So deadlines April 16 is the project proposal. So 4 pages seem to be okay, but you can use more or less. Just it has to come across what is the background, what is the problem, and what approach you're going to choose. Okay, so this has to be expressed. If you need 8 pages, it's fine. If you need 2 pages, also fine. And May 19th is the deadline for all deliverables. Okay, so we're gonna do this way. We're gonna do it this way. What you're gonna do for your for your project, you're gonna do a Medium blog. Okay, hopefully you all know this Medium platform. Okay, like Medium, it's easy. It's a very beautiful platform, right? It's a Medium, and you can log on. It's free. Okay, you start a blog there, and you tell me what in your proposal. You tell me what is the link to it, right? And you write about what you can start with a proposal. You can put that in Medium blog. So actually, you don't really have to, you don't have to send me a proposal. You can just put it in the Medium blog, then send me the link by email, or put it on Blackboard, and just keep writing what you do. Keep adding. What's nice about a Medium blog is, right, this can be like a nice thing you can use for your job search, right? Because now you got something that you can show, right? It's like your own blog and your own project that you've done, right? And you can link a YouTube video to it. You can put easily images into it. It can be public or private, whatever you like. And we can look at it. Your peers can look at it. Of course, you don't have to show them, right? But I'll keep all these links separate. You don't have to make it public if you don't want to. They can also be private, right? Only I know it, and the TAs know it. No matter how I matter you. But anyway, what's nice about this Medium is it's a nice platform to write things, and images go well into it. Snippets go well into it. You can link things to it. Like if you have a implementation you want to link to it, you can, whatever you like. You can all do that, right? And at the end, what I want you, not only I want the blog, but also what you want to have is like a single poster slide that summarizes everything you have done, and the video that shows how it works, right? So, so that's the minimum I want, right? If you want to make a GitHub, you can do that. It's up to you, up to you. You can do or not do it, but anyway, but be aware, if you put the GitHub out, right, people may copy it, right, and use it the next time, so in the class, right? So there's pros and cons. So I actually don't really, I don't really encourage you to do that, but if you want, you can, right? But for copy protection, right, the next time I'll then I have to compare all the GitHubs with with the next generation of students, right? So that's a little bit of a challenge. So here's and this is groups of 2 are okay. So you can have groups of 2. Just let me know who they are, okay? And then, so what I want you to do is I really want you to tie your project to something people really care about, right? You can go to this web page here. Okay, this is like a web page that I found. What people care about, right? So what people care about is really safety so this is actually based on a survey a pretty good survey, right? People care about safety from abuse, violence, coercion, threats. People care about healthcare. People care about nutrition, a variety of quantity food and beverage. People care about housing, employment, wealth, education, liberty, democracy, justice, including fairness, mobility, environment, and that includes everything, entertainment, community, and so on, right? So try to sort of get some data that, maybe you find another thing that people care about, but these are the things I found, that sort of educates that resonates with people in these kind of ways, right? Where really you create basically something that people can connect with, right? In these kind of way, in these kind of dimensions, right? So what I want you to do is really, it's an alternative to the visual data science. So, okay. So they make a proposal for a project. I don't think I'll erase this. I don't know what I mean by this. So don't look at this. So my proposal was that uses visual analytics within a wide application to address a specific problem, uses it for better data understanding. It can be a new visual analytics tool. You don't have to stick with something that it doesn't have to be, but it can be. Interactive single screen dashboard. That's what it really should be, right? I want single screen, okay? People should not have to scroll, okay? No scrolling, no switching to other visualizations. Single screen dashboard, and these elements, they interact with one another, right? It's really a single, I don't want any more things that you have to scroll through things or different sources, right? Different web pages, right? One single screen with a dashboard that has everything you want. And people interact with it by link brushing, okay? And we'll learn about link brushing next lecture. So no scrolling, all elements must be visible at all times, right? All elements must be visible at all times. No scrolling of the web page, okay? And the web page can fill the whole screen, that's fine, that can be fine. That is desirable, right? And you can, it can be a new theory, algorithm, or method. If you develop something really good, then you don't have to do the dashboard, right? If it's a new theory algorithm, right? Then you basically focus on a different kind of, threat. But most people probably choose this. Some people want to really invent something new. Then it doesn't have to be, right? So really two paths, right? And what I really also want, a good mix of standard and non-standard visualizations. Don't just have bar charts, pie chart, line plot, scatter plot, and so on. Also include something that is not so conventional, okay? Like MDS plot, PCA plot, MCA plot, multiple component analysis, power coordinate. Have a mix of it, okay? Don't just only bar chart, because otherwise, what have you learned, right? You have not learned anything, right? Because not using any high-dimensional data visualization techniques, right? I want you to use at least one or two of these two and put them in your dashboard, right? Of course, they already by itself, power coordinates by itself is already interactive, and you could think they're brushable and so on, right? But connect the power coordinate display with the other things, okay? You can have a data table if you like, that's also true. So this is basically what I expect you to do, okay, for your final project. So don't take it lightly, okay? Really think about it and make this a dashboard that uses link brushing and really gives a good sample of what you have learned in this class, okay? Really put everything in it, right? Find a use for it, okay? There's always a use for one of these, right? So next time I'll show you like a dashboard that someone developed, actually an undergraduate student that is really a good dashboard. I also show you some other examples that students have developed in the past to give you a little bit of an idea what I'm looking at or for, right? But I'll show that next time. Okay, I just want to give you like an introduction to this final project. Okay, so you can already think about this kind of topics that you may want to use, right, and so on, right? You don't have to yet decide how you're going to do it. First, decide the topic, right? It gives you and really this has to be done by the 16th of April. Okay, 4 weeks. Is it? Yeah, 2 weeks from now. Okay. So, okay, I don't see. Oh, okay. There's a chat here. What is the team size for final project? 2, right? Two, not more than 2. If there's 3, then people start to, one person falls off and the other 2 do all the work, right? When it's 2, it's okay. Of course, if someone does it by himself or herself, then it's, you don't have to do a lot. You have to do less than if you did 2. But if you do groups of 2, then you expect to do a little more than a group of 1, right? Of course, that would be expected. But group of 1 should also fulfill all these requirements, right? But may not have everything. May not have perfect, maybe like a little bit limited, than a group of 2. right? So that's basically all it is. Okay, so I'm going to give some more time for the dashboard. Sorry, for the chat. If there's nobody else asking anything, then we'll stop here and then continue next time. I recorded the video, so everyone should be, and I put it again on YouTube, and I send you the link on Piazza. Okay, so no more questions. Okay, then see you what is it, next week. Stay safe, okay? Please don't get infected, okay? Hopefully you're all doing fine. Okay, bye.